Good day, good afternoon, good morning, good night, everyone around the world. Welcome to another webinar on LDACS in a series on this new aviation communication system. We have 186 participants at the moment and still rising. So I will just, as an introduction, give a little reflection on the objectives. We have been working in the SESAR program on LDACS as a new technology to provide broadband communication from an air-ground data link perspective. We are working to increase the awareness around the world of this solution, which looks very promising. Knowing though that it is not yet selected as the option that we would aim for. It is one of the options. We just think that from all the research and validation results that we are gathering at this moment, that it looks very promising. So this is one of a series of 4 webinars. We did the previous one on the 23rd of April, which was a general introduction. IATA, ICAO, the FAA were there. Then today we are aiming to address all the technical questions that were not answered during that first session on the technical details, the architecture, the capabilities, the performance aspects. So it is going to be a very technical session. So get ready for that. You'll notice that the style is going to be a bit different from the let's say, relatively relaxed introduction that we had last time. You'll probably also come up with some questions about deployment, about transition, about the cost-benefit analysis. Be aware, though, that there are going to be two more webinars coming up. So in the 1st of July, we're working on the deployment and the transition scenarios, and then in September, we're preparing for the CBA, the business and economic considerations. Well, probably all of you have attended already the previous one, so you know the rules of the game. There is on your screen a chat function, which you can say the hello and goodbye, but there is also the questions. The questions is the tab that we as panel members are looking into and will either answer online, live during the session, or during the questions and answers at the end of this session. And those that are not answered will be answered later on offline and published with the WebEx recording. So also for the previous webinar, the recording is available on the SESAR website, including with the questions and answers that were addressed. Then today's speakers. So we have 4 speakers prepared for you. The first is the ANSP perspective, Maria Goretti Ruiz Cruz from INERA, which is a joint presentation, or let's say it's a presentation by Goretti, but it's jointly prepared with Ricardo de Souza from NETS and Klaus-Peter Half from DFS. Then we go on to the LDACS capabilities, presented by Michael Schnell from DLR, LDACS Architecture Overview, Simona Piratella from Leonardo, and then the LDACS technical details from Bernard Heinel from Frequentis. So I will introduce to you the first speaker now. Wait, I should have done that slightly different. Where is, yeah, Goretti. We'll stop sharing mine. So Maria Goretti holds a telecommunications engineer degree from the University of Vigo. She has provided technical support to INERA for the last 15 years as data link system expert. She is part of the data link deployment team and participates in the definition of the strategy for the implementation of new air-ground technologies in INERA. Goretti, the floor is yours. Go ahead.
Thank you very much, Ruben. I don't know, can you see the screen? Can you hear me?
Yes.
Yeah, great.
I can also hear you.
Let's go then. So I will talk about the ANSP perspective, and this is the, good morning, good afternoon, everyone. Thank you very much for being here today. So this is the agenda for my presentation. I'll try to explain first what are the needs that the NSPs have in terms of communication means. Then I will talk about how we meet those needs today. How are we going to face the future, and how LDACS is present in this future. Then we'll talk about how LDACS, or what benefits will be provided by LDACS to the ANSPs. And it was also mentioned by Ruben that there are other technologies that could also provide these benefits, and that are important to provide the new services that we are envisaging in the future. Next, I will talk about the LDACS service model from the NSP perspective, and the last point will be the conclusion of the presentation. So what do we NSPs needs in terms of communication means? The NSPs, the air navigation service providers, are legal entities, public or private, that provide air navigation services to the airspace users. And they are certified for that purpose. We provide air traffic management, communication, navigation and surveillance systems, meteorological service, and those services are provided during all the phases of the operations: approach, airdrome, and en route. To provide those services, we need to have the appropriate communication means. So, taking in mind that safety is our priority, there are all other aspects that are of paramount importance for us. For example, performance. We must ensure that a specific performance that guarantees that the services are being provided with the required quality. We can talk about availability, integrity, reliability. Also, our communication means has to be ready for support these new services. We are referring to capacity. Regarding security, the modernization of the European ATM moves toward the automation and the digitalization, and it will require an additional effort to guarantee the security, and in particular the cyber security. We have to keep in mind that there will be more and more systems connected, and it will increase the probability, the possibility of the cyber attacks and the vulnerabilities. Also, we have to ensure that the solutions we deployed are compatible in order to boost and to foster the competition among the industry partners. And also, we have to guarantee that those systems or those services are compatible with existing protocols and with the future ones. As we are providing more and more demanding services, also our networks has to continuously grow and improve. So it's very important. This is why scalability is a very important concept. And the last but not least is the cost efficiency, but take into account that we cannot run with unlimited cost. So it's important that every time that we make a decision, it has to be backed by a positive business. So to sum up, the goal of the NSPs is to provide the best services with the best quality, and always keeping in mind safety. Okay, so what do we have today? From the point of communications, okay, we are providing voice and data communications. On the ground side, our legacy technologies has already been migrated to IP, and with our IP-based communication systems. We take benefits of the advantages that IP networks can provide us, for example, reliability. The ANSPs demand more and more reliability, and it can be achieved through different ways, like dual core networks. And also we have to keep in mind that the new services, the new concepts that are being deployed in the future require more bandwidth, and it's something that we can guarantee with these IP networks. As you can see in the picture, we count on the new pens, IP networks, and we are connecting all the systems and all the services in the proper way. So we are ready for the future in terms of ground communications. But in the air-ground side, when we talk about the air-ground communication, maybe the first ideas that come to our mind will be congestion, interference, low quality, but these are consequences of the current technologies. as we know, the RF frequency spectrum is a scarce and limited resource. So for coping with, to overcome with the congestion and in the VHF voice channels, we are moving reducing the separation between channels to overcome this limitation in the medium and long term. We are going from 25 kilohertz of separation to 8.33 kilohertz of separation. If we talk about data link communications, we are using VDL Mode 2 networks for providing both AOC and ATC services. And this network, with the VDL Mode network, even when we are counting today with 5 channels, if we want to extend its viability, we will need to count with more channels in the future. But in any case, we have to keep in mind that we are talking about 31.5 kilobits per second. So it won't be possible to cope with these new and more demanding services. And it's a fact that is already reaching its capability in the areas in Europe with high traffic. Okay, so how we see the future in the ATM master plan is a planning tool for the ATM modernization in Europe. Let me see. I think you can see better now. As you can see, there are different arrows per technology. You can see in the current HF data, VDL Mode 2, SATCOM Class C and Class B. Those technologies are grouped under functional domains. These are trajectory recognition, airport positioning, and guidance for airport, airport position and identification, aircraft position and guidance for airport access. And there are also arrows, color arrows that represent the framework in which those technologies will be implemented. We can see that in the near future, LDACS is part of the performance communication base, performance communication, with Aeromax, SATCOM B, and also VDL Mode 2. And in the long run, it will be part of the performance-based CNS, and take into account that it is even when the main functionality for LDACS is communication, this functionality can be extended to provide navigation functionalities. Okay, so in the previous slide, as I mentioned before, LDACS was grouped with other technologies, with other ground technologies, in a concept that is called the multi-link concept. This concept has been widely discussed within the SESAR program for a long time, and generally speaking, it consists of the combination of different ground technologies to support safety critical applications. For the time being, those technologies are LDACS, are SATCOM, and are Aeromax, and there could be more in the future. What functionalities are associated to this multi-link operational concept? The evaluation of the link status, the decision on the link usage, and also the seamless handover from one link to the other. But there are several technical challenges that has to be solved for implementing this concept. Between those technical challenges, we can talk about, for example, the maintenance of simultaneous connections open on various links, and the routing issues that could be introduced on the ground segment. But in any case, we have to keep in mind that LDACS will be a very important technology within this multi-link concept. Okay. Next one. If I ask you to describe LDACS, and you have participated in the previous webinar, I think all these ideas will come to your mind. We will talk about secure communications because we will be able to provide that with encryption and automation. We will be able to provide or to use broadband applications. We're talking about for the track, meteorological maps. The granting quality of service, the prioritization of the applications will be possible. It is a multifunctional system because we are not only providing communications, but also navigation and surveillance. we can think about spectrum efficiency. It's scalable. It's based on a cellular structure. All these concepts have been explained in the previous webinar and will be also explained in more detail in the following presentations. But as you can see, these capabilities or those characteristics could be also fit with the key concepts that I presented at the beginning of the presentation, with security, with capacity, with scalability. So it means that LDACS is a technology that could cope with the necessities that we have in this moment in the ground link for the ANSPs. So from the communication point of view, with LDACS, we will have IPS communications, more channels available, bigger bandwidth, more capacity, and it will be translated on being able to provide more demanding services, new more advanced functionalities like encryption, authentication, and to provide better performance and more reliability. And this can be translated that we could be able to reduce the minimal separation and to handle more traffic with a better overall service. So is LDACS the only option, or is there room for other technologies? Nowadays, we have VDL Mode 2, Iron Max, even when Airborne Max is deployed in very few airports and not for ATC communication purposes, only for the ground vehicles communications. We have also SATCOM Class C, and we have other technologies that are not developed for aeronautical purposes, like 3G or 4G. What we will have in the future? Probably the use of VDL Mode 2 will be residual, and the natural evolution would be LDACS. It will provide more capacity. We are talking of 50 times the capacity provided by VDL Mode 2. We will have, hopefully, Airborne Max more widely deployed and used for ATC communications. We will count on SATCOM Class A and Class B. And there will be also the possibility to use the commercial technologies, 4G, 5G, even 6G, for these safety critical communications. This is something that is already studied within SESAR in the Project 14 Solution 61, when they analyzing the possibility of using these commercial technologies. But for doing that, those technologies have to fulfill different requirements. We're talking about security, safety requirements, security requirements, certification requirements. But these new technologies would also provide us with new benefits, but we have an improved capacity, a global coverage, interoperability, flexibility. So this is something that these are technologies that have to be kept in mind for the future. So the answer to this question, is there room for all these ground technologies? Yes, the answer is yes, but we need a rationalized approach and deployment. So as you mentioned before, this cost-benefit analysis, this positive business case will be very important to make a decision on the future of the ground technologies. So, regarding the LDACS service model, probably we have already answered the question in the chat, as it was also in the previous webinar. But in any case, as this is a topic that will be further explained in the next webinar, I'm not going to get into much detail. So you have to keep in mind that the deployment model and the service model are very related. We can think about three possibilities for the deployment. One of them would be follow a VDL, the model that was followed for VDL deployment model. In this case, it would be the CSP who will lead the deployment of LDACS in Europe. The CSP could take advantages of the experience and of the extensive VDL network that they have already deployed. And we can think that LDACS could reduce these sites. Another option will be that the ANSPs will undertake the deployment of the LDACS network. What is the rationale for this option? As I mentioned before, LDACS is not only used for ATC and AOC traffic communications, but also for navigation and surveillance. So it could be one option. And the third one, there could be others, but the third one will be a centralized deployment and service provision. The idea would be that the organization that will be in charge of providing the data link service in Europe could also undertake the deployment of the data link, the LDACS network across Europe. All these three options have its pros and cons, and in any case, more information will be provided in the next webinar. So now I almost reaching the end. So these are the conclusion for my presentation. That the NSPs will have to provide new services, and we need to keep the performance, even improving it. And LDACS will be there and would be useful as an additional add-on technology. LDACS not only provide ATS and AOC communication, but also supports navigation, probably in the future surveillance services. And we have to mention also the digital voice. We can see LDACS, that the natural evolution of current VDL Mode 2 network, providing a bigger bandwidth and better performance. And as I mentioned before, 50 times the capacity that is already providing VDL Mode 2. LDACS will be part of the multi-link concept, being a significant pillar of this future implementation. And also we have to remember that the deployment of the service model will heavily depend on the deployment strategy that we follow. And with that, I have reached the end of my presentation. Thank you very much for listening, and I hand the floor to Ruben. Thank you.
Thank you very much, Goretti. That was well done. I noticed that while you were speaking, you did it so well that we actually have more than, I think, 120 people more than when you started listening in. I also noticed that on the questions, a lot of questions that are being triggered by your presentation are probably going to be answered in the next presentation. So I do also need to see for the audience, check the answers that are already being given online. But anyway, I think most of those will be addressed in the later presentations. So thank you very much, Goretti. We'll continue with Michael Schnell to present on the capabilities. I will introduce Michael. Michael is the head of the Aeronautical Communications Research Group at the Institute of Communications and Navigation of the German Aerospace Center, DLR. The main research topics of his group are the development and modernization of CNS technologies for civil aviation and unmanned aerial systems. In 1997, Dr. Schnell earned a PhD degree for his work on wireless communications. He is a lecturer for multi-carrier communications, as well as for aeronautical communications, and acts as selected advisor for the German air navigation service provider, DFS, on various committees at Eurocontrol and ICAO. As rapporteur of the project team Terrestrial Data Link within the ICAO Communications Panel, he is also organizing the international LDACS standardization. Michael, I give you the floor.
Many thanks, Ruben. Also a warm welcome from my side to my presentation about the LDACS functionalities and capabilities. This presentation has been prepared by my colleagues, Thomas Kreubel, Okwari Osicas, and myself. And I would like to start with a brief LDACS overview. As you know, LDACS stands for Airborne Digital Aeronautical Communication System and is the upcoming broadband and secure terrestrial communication system for aviation. Interestingly, it was originally designed under a Eurocontrol contract, but then further developed in the framework of the joint FAA-Eurocontrol Future Communication Study. We heard already about that in the first webinar from Brent Phillips from the FAA. Now, LDACS is being refined within SESAR 2020. And it's important to note that LDACS has exclusively designed for aviation use in protected aeronautical L-band with AMRS allocation. LDACS is also, was already mentioned by Goretti, is already well positioned in the SESAR's ATM master plan, and is an essential part of the future communications infrastructure, and is also well reflected in the ICAO's Global Air Navigation Plan. Currently, LDACS is under ICAO standardization within the communications panel. And with that, LDACS is not a fancy future research project. LDACS is a mature technology for aviation, and we already have performed first flight trials in March, April 2019. Now let me explain some LDACS system characteristics. I think it's noteworthy to say that LDACS is especially designed for aeronautical communications. So in the design, we have taken into account the aeronautical channel characteristics with its high speeds, large Dopplers, and the large coverage areas up to 200 nautical miles. And we also have adjusted the design to the protected aeronautical L-band environment with its existing CNS systems there. We also had a look at the current aeronautical communication systems and their deficiencies and designed LDACS to overcome these deficiencies. So LDACS makes available a secure data link and voice communication. LDACS uses state-of-the-art technology as used in modern mobile radio communications. It is based on the orthogonal frequency division multiplexing technology, which is a multi-carrier technology, which is a highly flexible and scalable technology. LDACS also makes use of adaptive coding and modulation together with interleaving. That means that we not only cover standard QPSK modulation schemes, but also higher modulation schemes like 16 QAM, 64 QAM, and we also use concatenated coding. And with that, we can reach higher data rates. So as shown in the box, in the green box, there are the main LDACS parameters. So we are using 50 subcarriers. And that gives altogether an overall bandwidth of 500 kilohertz for one LDACS channel. Subcarrier spacing is around 10 kilohertz. And with that, we can achieve a net data rate, that is the data rate which is available for the user, of already 550 kilobit per second for QPSK modulation. And this boosts up to 2.6 megabit per second for higher auto modulation schemes and less strict coding. With that, we
Michael,
have... Yes?
Can I just interrupt for a moment? I noticed that there's a question here related to what you just mentioned, the net data rate that you just mentioned. Is that for per aircraft, or is it shared between multiple aircraft?
This is always a complete capacity as given in all communication systems. So if you have several aircraft transmitting simultaneously, you have to split it up, of course. And the ground station can make available this data rate.
Yeah, okay. Thank you very much.
Yeah. Okay, so with that, we have at least net data rates which are at least 50 times the medial mode 2 capacity. What's also important to note, I think, is that the deployment will be done in coordination with the existing L-band systems. For that, we have already included out-of-band radiation suppression techniques in our transmitter design, and we have integrated mitigation techniques, interference mitigation techniques in the LDACS receiver, and we will use frequency channel planning and LDACS station siting to achieve this coexistence in the L-band. LDACS uses a frequency division duplex approach, as shown in the picture with the frequencies there. We have a forward link and a reverse link. The reverse link is put at the lower part of the L-band and the forward link in the upper part of the L-band. We also use a cellular communication concept, which means that neighboring cells use different frequency channels. And with that, faraway cells can reuse LDACS frequencies. And we are planning to have a frequency reuse of 7 for this LDACS deployment. Now let's come to the functionalities. So let's start with the communication functionality. Of course, communications is the main LDACS functionality. LDACS has been designed for communication. With that, we can achieve the following communication capabilities. LDACS makes available broadband connectivity, which is very important to enable modern ATM concepts. This is possible because we are basing our design on modern mobile radio technology. And with that, we can achieve these high data rates, which are 50 to 250 times VDM02 capacity. LDACS also makes available improved communication performance and overcomes current deficiencies. We make available not only data link connectivity, but also digital voice. Some words about that later on. We have also a low latency transmission through coordinated channel access. We are using service priorities to ensure low latency and high continuity of service for safety critical ATS and AOC. And we do not have co-channel interference problems as experienced during the VDM02 deployment. LDACS has also built in cybersecurity means for secure transmission. That means we are ensuring mutual entity authentication. We protect confidentiality, integrity, and authenticity of messages, and we ensure availability and continuity of service. Supported network protocols reach from ACARS over OSI to IPS. Some further capabilities and applications which can be done within the communication functionality. I think it's very important to note that we can make available simultaneous transmission of ATS and AOC services due to the priorities we have introduced into LDACS. With that, it's possible to have high volume AOC data while ensuring immediate access for safety critical services. LDACS covers ADNB1, ATSB2, as well as emerging ATSB3, and LDACS is expected to comply with required communication performance, required surveillance performance, at least up to the emerging RCP60 and RSP60 requirements. LDACS is also foreseen to additional cover future services to enable ATM modernization due to this large capacity LDACS can make available. For example, full 4D directory-based operations, flight-centric ATM, and a secure connectivity to the flight deck. There are also additional applications LDACS extends into, and one very interesting, in my view, is that LDACS also enables single pilot operations through supporting respective applications. So if you have a single pilot operation, you need some support from the ground, and LDACS might be the tool to make available these applications. This can reach up to a command and control data link in case the single pilot on board is incapacitated. LDACS also extends into the navigation domain with its communication capabilities. LDACS might make available secure and improved GBus functionality. Instead of using the VHF data broadcast as it is used today, we can make available a GBus service via LDACS, and we can then cover also multi-constellation, multi-frequency GBus. LDACS also extends into the surveillance domain. It covers ADSC, including EPP. Now some words about LDACS Digital Voice. LDACS Digital Voice technology builds on the established voice over IP technology in the ground network. So a voice gateway connects LDACS to a standard voice over IP area and the voice over IP communication system behind that. And on the other end, the communication between the ground station and the airborne station is handled in the following way. The ground station has direct access to the resources, so it's quite simple to transmit digital voice from the ground station to the aircraft. That can be done in a broadcast manner or in a multicast manner or in an addressed manner. The other way around is a little bit more tricky because before a pilot can connect to a ground station, you need to reserve the resources for doing this digital voice transmission, but this is something which can be done straightforward. What's also very interesting with respect to LDACS Digital Voice is that the digital voice channels are independent from the physical LDACS deployment. So what we can have is we can have one LDACS ground station that can serve multiple ATC voice sectors. We can also have the other way around. That means one ATC voice sector that can be served by multiple LDACS ground stations. And we can have it completely independent of the current ATC voice sectors, meaning the establishment of flight-centric ATM, where one aircraft is directly assigned to a single controller over a huge area of control space. Okay, now let's have a look at the already mentioned LDACS navigation functionality. So navigation, of course, is a secondary LDACS functionality. and is foreseen as a backup to existing navigation means. So LDACS is foreseen to cover APNT, alternative positioning, navigation, and timing. And this can be done by LDACS completely, or it can be done in a so-called modular APNT approach, where LDACS is one of the important sensors for APNT, but we also use other sensors like DME, parametric height sensor, or inertial sensors. We see as a requirement for APNT that we need to achieve RNP1 widely, and where needed even RNP03. And these requirements are just what LDACS can also deliver. And the nice thing is that this comes on top without any changes to the original LDACS signal required. The only additional requirement for the navigation functionality is that we need a more precise synchronization of the LDACS ground stations. Whereas for communication, it is sufficient to have this synchronization in the order of microseconds. For the navigation functionality, we would need it in the order of tens of nanoseconds. But that can be done with GNSS discipline low-cost rubidium atomic lock, which runs free in case of GNSS outages, or with a fiber optic time transfer. But how does this navigation functionality work in principle? So actually, the basic principle is quite simple, because LDACS ground stations transmit all the time. And with that, if you have a source transmitting all the time, you are able to synchronize to the signal, and with that you can do pseudo-ranging to the ground stations. And with that you have just the same situation as you have for GNSS. The only thing is our satellites are the ground stations on ground, and they act as pseudolights. This concept has been proved long years ago using theory and simulations. And it was possible to show that in theory very high accuracy can be achieved, and in flight trials it was possible to show that we can achieve very interesting accuracies in the range of 20 meters for the pseudo ranges and 80 meters for the horizontal position. I brought some results from one of the flight measurement campaigns we did to show here. This was a flight measurement campaign performed 2018 with an experimental temporary LDACS deployment, where we put 4 ground stations in the southwest of Munich. And as long as we were flying within the area spanned by these 4 LDACS ground stations, it was possible to bound the horizontal position error with a 95 percentile with around 80 meters. So we were able to achieve RNP03 as long as we are in the coverage area by the 4 ground stations. If we extend our flight path beyond that area, it was we were able to show that we still can achieve, in this very simplified constellation, we can still achieve RNP1. Okay. Now coming to this summary and outlook. As I showed, LDACS covers communication as a primary functionality and navigation as a secondary functionality. LDACS makes available secure broadband communications, which is heavily required for the CNS ADM modernization currently taking place, for example, within NextGen and SESAR. LDACS offers APNT almost for free and covers also surveillance applications like ADAC EPP. And LDACS has the necessary capacity and performance to enable ADM modernization and to deliver APNT. Let me finally give you some outlook into the upcoming work. This year, additional L-band compatibility testing is planned to derive final frequency planning criteria. And in the summer next year, additional validation flight trials for LDACS are planned within SESAR 2020. And by end of next year, LDACS is expected to reach TRL 6. The ICAO standardization is ongoing, and we envision applicability of LDACS in 2024 currently. I think that's all from my side, and I thank you for your attendance and questions later, I guess. Thank you.
Thank you very much, Michael. Indeed, I guess we'll do the questions later. There are plenty of questions, so feel free to start already answering them online while we continue with the next speaker. The next speaker is Simona. Where is Simona? There you are. The next speaker is Simona Piratelli from Leonardo. So she's the project manager for our current project, our as in SESAR Wave 2, on integrated CNSS. Working in the environment of aeronautical radio communication for the last 10 years, designing and developing the new L-band data link, actively contributing in the standardization of Aeromax data link and in the definition of data link system specifications. Since 2012, she's been contributor to some SESAR projects, for example, those that are related to airport service data link Aeromax and to enhanced service guidance. Simona will, well, as already shown there, elaborate on the architecture of LDACS. Simona, the floor is yours.
Thank you, Ruben. Welcome. And with this presentation, I would like to give you an overview on the LDACS architecture. The architecture for LDACS around data link was defined and validated starting from SESAR Wave 1 in project 140201, and during the next phase of SESAR Wave 2, Solution 60 continues working on this validation and also with the updating of the architecture. The design work is also shared with the ICAO PTT working group. What are the principles that driving this design? First, LDACS shall support the new FCI infrastructure, shall support digital voice communication, both for sector-oriented and flight-centric operation. The architecture shall support the deployment of LDACS technology supporting legacy systems like ITN, OSI, and ACARS. Is a data link in the L-band digital aeronautical communication system that shall provide a secure wideband data link for data and voice services. LDACS shall overcome the current limitation on the VHF data link mode 2 and also support new services like AirPass shall support navigation services and shall support the current ITN B1 and B2 services, as well as the next SWIM purpose profile. LDACS is composed by two segments, the ground segment and the aircraft segment, and all the two segments shall support the following external interfaces. The interfaces for the ITN IPS messages, for the digital voice communication, for ITN OSI, and for the ACARS. How is composed the ground side of the network reference model? The LDACS access service network is composed by ground station, the ground station controller with the functionality of the routing and the communication with the authentication, authorization, and accounting server to ensure the security and the encryption. So the LDACS access service network provides the following mandatory function: the connectivity with the aircraft station, the transfer of the authentication and encryption messages with the LDACS subscribers on network service provider, and the network discovery and selection of the LDACS subscriber with the preferred NSP, and also the radio resource management. In addition, for a portable and mobile environment, a ground station controller shall support also the anchor mobility and the location register. What are the interfaces that the ground side shall support are, first of all, the interface between the ground station and the ground station controller. That could be logical and physical interface. This interface consists of the set of control and user plane protocols for communication between the ground station and ground station controller, and it is the messages are not only the messages related to the control plane, but also the messages related to the user plane. Then there is another interface that is G2 that give all the ground station the possibility to exchange control plane messages, and then the third interface that is the one that ensure the security and authentication feature, and consists of all the messages that the ground station controller shall transfer with between the authentication, authorization, and accounting server. On the Airborne side, there are three main functional blocks. That is the aircraft radio, the LDACS Airborne Voice interface, and the LDACS Airborne Network interface. These three logical function shall ensure the connectivity with the ground station, the possibility to discover a network and select the proper ground station of the preferred NSP, and so register on the network, and also the relay functionality for establish NL3 connectivity with an LDACS ground station controller that, for example, is needed for IP address allocation, and then also ensure the radio resource management. These three functional blocks give the possibility to support all the external interface that we have seen in the first slide. What are the interfaces between this block? A0 and A3 are the interface that has in charge the communication, the exchange of the message related to the digital voice communication, while A1 interface is the one that permits to exchange all the protocol messages that manage the connection between the access network interface and the Airborne radio. So all the messages that are proper of the LDACS are ground data link and permit to register on the network, authenticated on the network, and then exchange all the data. And then there are all the external interfaces that need to support all the services that can be ATN IPS, ATN OSI, and ACARS communication. The working group AATF is collecting all the requirements for the LDACS system, with the goal to finalize an easy installation and integration of the LDACS Airborne into various aircraft systems. The general goal is to have minimum changes on aircraft. This is to facilitate the first deployment of the LDACS phase and also to reduce the cost. And also, the new ARINC standard may need to be developed as consequence. In this group, two possible options are under analysis, and the first one is to have a single box where integrating VDL Mode 2 radio together with the LDACS radio. And the second option is to have two separate boxes, one for the existing DDL Mode 2, and the second box is the new one related to the LDACS radio. These two options will be more in detail discussing during the next webinar. All the two have some benefits, and they should be better defined and analyzing. One of the most important feature, together with security, for that this new architecture shall support, is related to mobility. Two kinds of mobility is supported by LDACS to ensure that no data will be lost during the communication. The first one is related to handover and off, and the second one is related to network mobility. Two kinds of handover are is possible to be supported by an LDACS access network. The first one is handover type 1, and when a subscriber station, a ground station, announced to an aircraft station to hand over to another ground station, this air ground station will shut down the communication with the ground station where he is registered, and move to the other ground station. So the data link service manager of an air ground station shall be resetted, and a new instance is created when he is registering the new in the new ground station. With the second type of handover, this procedure is done without having a stop of the transmission. So the airborne station is registered in ground station 1, and linked to the physical parameter and the quality of the communication. The ground station 1 announced our ground station to move to the new ground station. The two ground stations are connected to the same ground station controller, and this permits that the aircraft station can move from a ground station to another without stop transmission and without no loss of data. The second kind of mobility that is defined network mobility is related to mobility that impact different LDACS subnet. During a normal registration authentication, an LDACS Airborne radio receive from the LDACS ground infrastructure the mobile network prefix that is assigned to an aircraft. The mobile network prefix is distributed into LDACS ground infrastructure so that this aircraft is reachable via the LDACS network. The LDACS air ground router announced the mobile network prefix via the external interface to the core EP network according to the used global mobility solution. So the LDACS provides within the access network a local mobility solution, transparent for all the global mobilities. The LDACS architecture is designed to be integrated in the new FCI infrastructure, and during the SESAR Wave 2 phase will be also validated in the LDACS infrastructure in FCI environment by Solution 77. And also there will be flight trial planned for the Q3 of next year, conducted by PJ33 Wave 2 Solution 2 that will validate LDACS architecture in an ITN IPS environment. So the LDACS architecture is not only defined during this SESAR phase program, but also validate in laboratory and in flight trial. Another functionality that LDACS shall provided in the next year is voice transmission. In a SESAR solution that is PJ33 Wave 3 Solution 2, we are working on developing operational and functional requirements supporting the current available operational method and process that are using the current VHF technology. This is baseline is the operational concept of the current analog VHF air ground voice services. So LDACS digital voice concept should be integrated in the existing voice infrastructure, nothing new. And the ED 137 standard should remain unchanged. So LDACS digital voice solution should benefit from the feature of a modern digital air ground data link like secure means, voice quality, the possibility to have point-to-point communication, but it will be integrated in the existing system. And a voice service for flight-centric operation should be also proposed. As you can see in the figure, there will be a new element that it will be introducing in the LDACS ground section, that is the LDACS digital voice gateway, that is the main equipment that will make possible to use the existing VoIP system with the new data link, the new LDACS architecture. The digital voice gateway is permanently assigned to a voice sector and provide the digital voice services for this sector, serving various DCS. The interface to the DCS is according to the Eurokai VoIP AD 137.1c radio standard, and the digital voice gateway has a list of LDACS ground station covering the voice sector. So a voice sector will be composed by many LDACS ground station. But a ground station shall also be connected to different digital voice gateway. And the LDACS ground station reserving the bandwidth for the voice channel on the air ground data link and confirms the R2S start messages. And this is possible due to all the quality of services mechanism that is one of the main features of the LDACS data link. The connection between ground station and digital voice gateway is monitored by using the R2S Keep Alive, and the LDACS ground station announcing the voice services over the air ground data link. Two options are now under analysis for the aircraft. There is the first option where the aircraft which want to use the voice services register on the LDACS ground station and will be confirmed for the possibility to use voice services from the ground station. And the second option that no registration of the aircraft is needed, but the aircraft it simply used the voice channel. This is my presentation. Thanks for your attention. I will leave the floor to Ruben.
Thank you very much, Simona. I see plenty of questions coming in. I also noticed that we are running behind schedule. That's a bit of a pity because there are really interesting questions that I would like to have in the panel session. But we have one more presentation to go from Bernard Heinel, and I think that will likely answer at least a couple of the questions that are being raised here. It's going to deep dive into all the technical aspects. So Bernard, let me first put you big on the screen so they can see your face. Well, it's a bit blurry, but at least to some extent we can see you. Bernard Heinel is working in the new business development department of Frequentis, which is responsible for LDACS. He received his PhD degree in electrical engineering from the University of Technology in Vienna in 2005. He has participated in several international aeronautical research activities focusing on safety-critical radio and IP communications. He contributes to a number of EUROCAE and ICAO working groups, including the ICAO Terrestrial Data Link project team, which is responsible for the standardization of LDACS. Bernard, the floor is yours.
Thank you, Ruben. So also a warm welcome from my side. I would like to present in the following slides the technical details of LDACS. And so for some LDACS subjects, I want to dive into the depths of the system, and other I will address at the high level only. I hope there is something for everyone in the audience. So I want to go to the next slide. Yep. Sorry for that. After Simona has addressed the functional architecture and the system properties of LDACS, in her presentation, I will also start with an architectural picture, but with a representation that shows a possible realization of the LDACS system. As mentioned already, LDACS is subdivided in areas. You have the LDACS Airborne area, a topic which will be covered in the next webinar, the LDACS ground area, where a possible implementation of the functional architecture is shown. You see here the LDACS ground station, the IPS and legacy access network for transporting ATN IPS packets and messages using legacy protocols like OSI or ACAS. The IPS part will be validated in the SESAR solution mentioned also already by Simona. The third part is the air-ground interface, which is just an interface, but the most important one in LDACS, since it is the basis for the performance and functionality of LDACS, and it guarantees the interoperability between aircraft and ground system. Therefore, I would like to discuss first this interface in detail. Then I will briefly describe the quality of service, mobility, and security functionality of LDACS, and finally I will address deployment relevant topics from a technical point of view. So here you can see a slightly different representation of the LDACS air-ground interface, and it isn't shown that it is an essential segment of the end-to-end air-ground communication from the aircraft down to the ATNS or AOCN system. The protocol stack on the top left shows the mapping of the air-ground communication protocol to the OSI layers. So the LDACS air-ground specification covers the physical and data link layers. And below you see the detailed representation of the LDACS air-ground protocol. Starting on the top, you see the sub-network protocol, which provides the interface to the network layers like IP version 6 or OSI or ACAS. The data link layer consists of two sub-layers. It's the logical link control layer and the medium access control layer. The logical link control layer is further subdivided in the voice interface, which covers the voice services, and the DLS is responsible for providing communication service with different class of services for the higher layers. The physical layer provides the means to transfer data over the radio channel, and finally you see the link management entity, which doing the cross-layer management for the whole LDACS protocol stack. Coming now to the next slide, I would like to discuss a little bit the essential requirements and the influences on the LDACS system design and why this makes it different from mobile communication systems. As mentioned by Michael, LDACS was designed for specific requirements of an aeronautical communication system in the L-band. So the physical layer parameters like OFDM sub-channel bandwidth, a location of pilot symbols, and the length of the cycle prefix, which is so some parameters of OFDM, were designed by considering the specific and special physical channel characteristics for communication in the aviation, meaning the aircraft speed, the long distance between the transmitter and the receiver, and so on. The framing structure, which I will present in the next slide, and the layer 2 design of the system considered mainly the performance requirements for transporting safety critical data. It considers latency, quality of service, security, and also robustness. A major requirement is the coexistence with the legacy systems in the aeronautical L-band. And this affected, among others, the spectral mask of the transmitter, the bandwidth, the coding, and the synchronization concepts. The resulting robust system is the main reason for the low data rate per bandwidth or bits per hertz if you compare it, the relative low, I would say, if you compare it with mobile systems. And as already mentioned, the efficient coverage of the airspace and the support of a very high user mobility had a significant impact on the LDACS system design. And since it was a question during the presentation of Michael, I want to also raise here the topic that the data capacity that is provided is always a trade-off between supporting future needs and efficiently deploying a system, since the range that you can cover or the cell size that you can cover with LDACS strongly depending on or limiting the data capacity, as well as deploying a system not in a green spectrum, sharing the spectrum with other legacy systems. So it was also necessary for the system design to address the limitations of the existing systems, such as lack of security or lack of deterministic channel access or the problem of detecting link losses. So, as already mentioned, the system is based on OFDM. Michael covered this. So in the reverse link, that means from the aircraft to the ground, the aircraft stations are separated by time and per frequency, and the ground station transmitting continuously OFDM symbols on the forward link, that means from the ground to the air. For coding, LDACS uses classical concatenation of an outer Reed-Solomon and an inner variable rate convolutional code with interleaving between and after decoders. The main reason for not using newer coding concepts is that the aircrafts typically have low data rate applications, and these new concepts are intended for high data rate applications. On the figure here on the right, you see an untypical presentation of a cell-based system. But the intention here was to show the use of different sized LDACS cells. The LDACS cell design covers large cells from up to 200 nautical miles. Seeing here in the remote area, you could have could be very scalable and have small cells in high density areas where you need more capacity, and you could have separated 40 nautical miles or 60 nautical miles cells as airport cells covering airports where you perhaps have more need for data. This slide addresses the air-ground interface framing structure. The picture below on the left shows the communication concept in LDACS, in an LDACS cell, where the LDACS ground station is the central element, and it coordinates the channel access on the forward link and on the reverse link, and with this it also guarantees limited duty cycles for each aircraft, which is important for compatibility in the co-site environment in the aircraft. The LDACS framing structure is shown on the right. And on the bottom, you see the forward link. That means from the ground to the aircraft. It consists of the broadcast channel, which is mainly responsible distributing the cell information, and it's needed for cell entry and cell exit. Then the remaining part is subdivided in 4 multiframes, And on the reverse link from the aircraft to the ground, you see the random access channels. They have 2 opportunities and also 4 multi-frames. The random access channel and the broadcast control channel are used for cell entry and cell exit, and the random access channel is the only one where the aircraft can access autonomously to the reverse link. All other reverse link transmissions are scheduled by the ground station. So each of the multi-frames is subdivided in a control plane and in the data plane. The control plane is shown here in green and the data plane in red and in blue. So in green you have on the reverse link you have the dedicated channel, and on the forward link you have the common control channel. These 2 channels are responsible for resource requesting resources and allocating resources to the different aircrafts. The dedicated channel is, as the name says, dedicated to each aircraft, and this enables a low latency transmission since each aircraft has the possibility, at least within a super frame, to get access to the reverse link and can request resources. And with this, we have also a keep alive, and we have the possibility to fast and reliable detect link errors on the ground, which avoiding fault link conditions on ground, which is an issue, especially for the multi-link concept, where you need to know the state of the different air-ground links. So coming now to the IP connectivity, mobility, and quality of service functions of LDACS. The LDACS provides an acknowledged point-to-point connectivity using selective repeat RIQ protocol and an unacknowledged communication, point-to-point and point-to-multipoint communication between the ground station and the aircraft. The unacknowledged is used, for example, for digital voice. LDACS supporting an ATN IPS mobility that is required for the IPS communication, and is supporting this natively, as already mentioned by Simona. During authentication, the LDACS ground system gets the mobile network prefix, which is assigned to the aircraft thanks to the ICAO working group I, which have chosen this concept. So with this, we can already, during a login, we can already announce to the IP network the reachability of the aircraft via LDACS. Locally, the local mobility solution is based on an overlay concept like Proxy Mobile IP version 6, which we're validating in the SESAR solution. And it's this overlay concept keeping the underlying IP infrastructure untouched. So with this, it's easily to deploy an LDACS system in an existing IP infrastructure. Regarding quality of service, LDACS supports quality of service by managing service priorities. This allows ATS and AOC services to be handled in parallel without affecting latency of safety critical applications. The used 3-stage quality of service approach is shown in the figure here. On the right, you see on the one in this light blue box, you see the standard, I would say, queuing, the multiple 3 queues, high, medium, and low, providing the quality of service based on the DSCP value. So here this box will classify the traffic according to the DSCP value and map it to the queues. Then the LDACS scheduler will use the traffic from the high priority queue before the medium and the low. So with this, if there's a congestion in the low priority queue, it will not affect the high priority queue. You have the same concept on the forward link on the ground station. So also the ground station will do this classification based on DSCP, and then we'll have the the prioritization and queuing concept. In addition, the second stage is that the LDACS ground station allocates the resources to the aircrafts, to different aircrafts based on the requested bandwidth and on the class of service that the different aircrafts are requesting. So that means there is a possibility to allocate resources to a specific aircraft, and not one aircraft can have the whole bandwidth. In addition, the third stage here is that we have the possibility to reserve for special services and applications, like, for example, for digital voice, we can allocate separate bandwidth. You see this here in the green boxes. That mean if you have a separate specific service like digital voice, you can reserve bandwidth for this on the reverse link and also on the forward link. It's the easier part. You can reserve specific bandwidth for specific services or for applications. Okay, coming now, one slide about security. The LDACS security architecture is in line with the work of the AEC IPS subcommunity and the ICAO working group I security subgroup. It is important that for this LDACS security concept that all entities in an LDACS network are authenticated to each other. To a certain, the only trusted participants can use the system. That means a prerequisite is that all the LDACS elements in the access network need to be authenticated to each other. And if an aircraft enters an LDACS cell, there is during the login, there's a mutual authentication required. That means the aircraft needs to be authenticated by the ground system, and also the other way around. The LDACS security is implemented on the subnetwork layer and is applied to all data sent over the LDACS. So that means it is an independent security mechanism independent of the higher layer. It adds an additional layer of security on the future communication infrastructure. It provides the capability to protect the integrity and privacy of messages in transit. This is optional, since this is for ATC. This is done end-to-end by DTLS in the upper layers. And on the control plane, it also protects the authenticity and integrity of the control data. That means control data that needs to be exchanged between the aircraft and the LDACS ground station for resource allocation, for example, in the dedicated channel or in the common control channel. Here on the picture on the right, you see the figure that all the additional security functions that are needed, that need to be done in order to provide these capabilities. I want to highlight here the group key management, which is needed to support the privacy, to support the integrity and privacy of the control panel, of the control plane. Sorry. This slide is now about the LDACS spectrum mask. To minimize the interference of existing L-band systems, the LDACS transmitter spectral mask is very stringent. The spectral mask falls very quickly. You see this here on the right figure in the out-of-band domain, and has a very low value in the spurious domain. The allowed power density here is 90 dB below the power density in the passband. So the high demands of the spectral mask can be seen best if you compare this with another system. And on the left, you see the comparison between LDACS and UAT, the other communication system in the L-band, and you see that in the spurious domain, that means 4 megahertz, at 4 megahertz distance from the passband, you see that the LDACS produces 42 dB less power density than the UAT, which is very important to provide the compatibility with the legacy systems. Okay, next is about the compatibility with navigation and surveillance means. In order to deploy LDACS in the L-band, we need to ensure that it will not impact other legacy radio systems operating in the same or in adjacent bands. So after several compatibility analysis and many simulations, the first LDACS compatibility tests were carried out in 2014 at the DFS labs. In the picture at the top right, you can see all the possible scenarios that were taken into account for compatibility. In all test cases, only the influence or the impact of LDACS on the legacy systems was measured. The additional influence of other systems would have been considered by appropriate margins during LDACS frequency planning. But after feedback and coordination with the ICAO navigation system panel, further LDACS versus DME TACAN compatibility tests were conducted in 2019, this time with aggregated interference scenarios. That means the impact of LDACS was measured together with all the other systems in the L-band, means with JT-Smith's background and DME background noise. Unfortunately, the background interference defined for the compatibility measurement has turned out to be overly conservative, and in addition, that means that also without LDACS, the device, the DME receivers were not fulfilling the required performance requirements, or the needed performance requirements. In addition, the DME equipment that was used for this test campaign was partly outdated. We used the same equipment as 2014. We thought that's a good idea to compare the tests, but yeah, this is 5 years later, and some of them, well, they were already outdated 2014, but 2019, they're not representing the equipment that's currently in use. So therefore, a new update of the test plan is ongoing together with the ICAO navigation system panel. The discussion with the surveillance panel started this year. Also, they have a very strict compatibility requirements which protect not only the system, but the spectrum. We see it less critically due to the large frequency separation that we have to the 1030, 1090 systems. Since Michael presented already the LDACS forward and reverse link spectrum, and we're running out of time, I think I will skip this part, the top of the slide, but I want to mention that the LDACS duplex spacing between the forward and the reverse link is 146 megahertz, which should make it easy to design a duplexer for that. And we have no fixed assignment between the forward link channel and the reverse link channel, which allowing us a dynamic allocation of the two links. The assignment between the forward and the reverse link will be distributed by the broadcast channel. The maximum transmitted power is 42 dBm for the airborne and the ground radio. That's roughly 16 watt. Regarding the reusing of the existing infrastructure and the deployment, for deploying LDACS, the reuse of existing infrastructure on board and on ground is a key to reduce the costs. So that means on ground that we combine, that it's needed to combine the technological advantages of LDACS with the existing VDL-Mod2 infrastructure. Such an LDACS transition concept will be presented by Sita in the next webinar. On the airborne side, the LDACS airborne radio has to support a combined and coordinated usage of LDACS and VDL-Mod2 in order to bring LDACS on board without additional antenna. The aircraft can use LDACS wherever deployed on ground, otherwise VDL-Mod2 is used. and this enables the gradual introduction of LDACS, starting where broadband connectivity is needed most. So, to summarize the presentation, LDACS considers all characteristics for safety-critical communication in aviation. It provides guaranteed data throughput and latency. With the large cell size, it covers the airspace efficiently, and the stringent spectrum mask allows the sharing of the aeronautical L-band with legacy systems. And I think we as aviation community need to use our spectrum efficiently to be able to deploy future aviation systems and to protect the spectrum. LDACS is the first candidate that requires such an active spectrum management, and there is, what we see, there is still room for improvement at all levels regarding this issue. LDACS is well established in the ICAO Global Air Navigation Plan and the SESAR TM Master Plan. It's well integrated into the future IP version 6 based communication infrastructure, and also provides connectivity with the legacy OSI and ACAS systems. LDACS extends VDL Mode 2, like for example LTE extends GSM, and complements the satellite links with a scalable high-performance ground-based communication system. With this, it supports the multi-link concept discussed at ICAO and SESAR. As a distributed system with no central single point of failure, LDACS is highly resilient, and the provided maintenance approach further reduces the downtime. Existing VDL Mode 2 radio sites can be reused for LDACS, which cutting the time and cost of deployment. So thanks. This will conclude my presentation. I'm afraid it took longer than planned, but thanks for your attention to such a technical topic. Thank you.
Thank you very much, Bernhard. You did a great job, as did all the other speakers, so thank you all very much. I realize indeed that we are way behind schedule. We had planned to have 30 minutes for questions and answers, and actually we already ran out of time. Before we go into a debate, because I do want to spend a bit of time on Q&A, but I also noticed that already well, we do have an audience that may have other commitments. I would like the audience to look at the poll. There is an evaluation of this webinar. We do that since a while to get feedback on how well or where we should improve on our webinar organization. So I would like to ask you to fill out that poll while we start the discussions. In order to start the discussions, what I will do is I'll keep an eye on the number of participants. If it drops below 150, we're going to end. So we had at some point 250. So it's up to the audience to decide when we stop, basically. I would also like to invite on stage those that supported Goretti. So Ricardo de Souza and Klaus Peter, you're already there. And I also saw Okwari Osache supporting Michael Schnell, if I recall well, on the APNT. Maybe Okwari, you want to join as well. I'm just gonna start straight away, knowing that we're not going to be able to answer all the Q&A. Most of the, or let's say the majority of the questions already have been answered online, but those that are not answered yet, we will answer in the course of the next days. So in a week from now, we will have uploaded the full set of answers with the webinar recording on the SESAR website. So those for you that are not able to attend for the rest, you will find the answers in about a week from now. I don't see the support speakers joining. Feel free to join the stage. We have more chairs available. I'm gonna start with maybe the most obvious question, since we are driven, first of all, by the need for having a better data link. I see some questions here about, for example, from Ben Willems. What latencies can we expect on LDACS compared to VDL Mode 2? And then similar, the RCP 130 and RCP 60, doesn't that still mean that it's the same performance? So what are we actually going to gain? Who dares to answer that one? Klaus-Peter, I give you the floor, or Michael.
Yeah, I was answering this question. I was trying to answer the question before. So the RCPs in particular includes also the human reaction on the pilot and the controller side. And if you look into the specification, which is the ED228, you will find that the vast majority of the time is really associated to the human reaction. I have to be honest, I cannot from the top of my head come up with the technical latency provided by the ones. It's in the frame of some seconds for VDL mode 2 as far as I remember. So it's not a big one. So out of this 130 seconds assigned for the overall communication, there's only a few seconds assigned to technology. And it's proven definitely LDACS is magnitudes better than that, but it does not really contribute a lot to the RCP at the end, because still the human reaction will not be speed up with the new technology.
Okay. Thanks, Klaus-Peter. I'm just digging a bit further into this, because I also see a couple of questions that raise concerns on the fact that the data link is not only going to be used for the safety critical information exchange, like CPDLC, for example, but also for AOC purposes. Now, I do notice that, Bernard, you mentioned the prioritization scheme, but I also get some feedback that, well, if everyone abuses the system by claiming that their message has high priority, it's going to fall apart anyway. Any response on that?
Yeah, from my side, as all other systems, if you request always the highest priority, you can destroy all the quality of service, of course. But that means that why we have this three-stage approach, that means even if the aircraft requesting always the highest priority, we will be able on the ground, since this is the master of the communication, to allocate traffic to the corresponding aircrafts. Since they're all requesting the highest priority, you have no way to decide which one really needs then the bandwidth or the capacity.
But I would expect that there will be some guidance about what type of messages we will have what priority, I suppose.
Of course, this is defined and standardized in ICAO on the working group I. So the applications, they are allocated different DSTP values, and we're using this DSTP values to classifying the traffic. And if there is one aircraft which is perhaps not, I don't know, it's reacting in a false way or acting in a false way, then you can stop this by from the ground, since you're allocating to them only limited resources.
To add to that, maybe a few words
Okay,
on
thank you.
a lot of the priorities are preset. So there is classes of service assigned already to different types of messages. And just to use a regular example, engine data, for example, is for sure not the highest priority, and there's normally not foreseen that there's any human interaction to set a priority. So the type of message determined finally is a priority, and if it's an ATC message, it's getting a high one, and if it's just a maintenance message, it's getting a low one or a lower one. Nevertheless, Bernard rightly pointed out at the end, even with running out of capacity, the system will make sure that the remaining capacity is equally shared about the highest priorities requesting it. So you will not be really locked off as with today's communication, where a big block of data can block the channel for minutes and no one else have a chance to intervene. That's not the way LDACS works, where you get in due time another slot to transmit your information.
Okay. Thanks, Klaus-Peter. Next question, different topic. Well, no, the topic is the same, but the nuance here a bit different on spectrum. Some concerns here in the questions about spectrum availability. Some eyebrows raising, like, really, do we need that much spectrum On the other hand, I see in the presentation from Bernard that you have actually pretty tight spectrum masks, which makes it spectrum efficient. Then there is also the dual use with the APNT, the digital voice, etc. So what is going to happen? Is this actually contributing to spectrum efficiency, or is this just a sales argument? Michael.
Okay.
How about you?
I'm the sales representative. No, that's not true, but I try to answer. Actually, it's not a sales argument. So the thing is the following. So we are aiming to establish the LDACS communication system in L-band, and L-band is already used by other ICAO systems. And we did quite a lot of design in order to achieve this coexistence with the already existing systems in the L-band. Actually, we are using spectrum, aviation spectrum, which is already used. So with that, LDACS is really spectrum efficient in that way. And as Bernhard already pointed out, we did quite a lot of work in how to be compatible with the other L-band systems. So we are not only making sure that we avoid unnecessary radiation into the L-band by having a very strict spectral mask. We also have implemented at the LDACS receiver certain measures to cope with the interference coming from the systems which are already deployed in L-band. So this is all taken into account during the design. And this is also necessary. If you would like to share a spectrum where you already have other systems, then you need to take these into account if you set up a system, a new system. And if you would now come with a, let's say, standard mobile radio system, then you would need to adjust this system to this situation as well. So there's not much gain to get back to one of the already existing systems, because you need a lot of adaptation to these systems as well. So I think LDACS is in that sense very spectrum efficient, because we are sharing already a used system, and I hope this answers your question. I try to sail a little bit.
Yeah. Perhaps I can add two
well,
sentences.
So I guess it. Yeah.
Go ahead.
Go ahead.
Okay. Perhaps I can add 2 sentences.
No,
As
just
mentioned,
wanted to.
we are not using the spectrum alone, and therefore we need, during the frequency planning, we need to do this coordinated with the legacy systems, the DMEs that also using this frequency band. That means we need more opportunities, more channels that we can choose in order to on the one side providing the capacity, and on the other side to minimizing the interference on the legacy systems. But as I said, we're not using any green spectrum only for LDACS. This is shared with the DME systems.
Yeah, I think there's also a link to the transition, but maybe that's for the next webinar. But so if I'm going to ask it anyway. So if LDACS can be used for APNT, but also DME is used for APNT, so the obvious question that comes in my mind is that on the long run, once LDACS becomes, let's say, fully available, has plenty of coverage on the data link side, does it mean that we don't need the DMEs anymore?
Shall I try to take it?
Yeah, go ahead. I see also Goretti. I think would be interesting to also hear an ANSP view there.
So, well, first of all, if you establish LDACS step by step, then you will have more and more ground stations, and with this you have more and more possibilities to do also APNT. As I mentioned in my presentation, APNT might be a modular APNT approach, where we not only use the LDACS signals for ranging, for pseudo ranging, but also other sensors like DME or the parametric height sensor or inertial sensors. And getting more and more LDACS station, of course, less DME stations might be required, and we might have a gradual switch over from the AP&D infrastructure, let's say. This opportunity exists in my view.
To add to this from an ANSP point of view, and indeed this opportunity exists, and Ruben pointed it out correctly on the long run, and I have to add on the really long run, because this means you can only switch off the DMEs entirely when you have converted all flying aircrafts, and we know this can take decades. So at the end, the opportunity is there, and it would be the more spectrum efficient solution, but it would also require a heavy investment in the legacy fleets, and this is not yet decided. It's premature to state this is a way to go. It's under discussion, but it would be in the long run indeed the best solution, because it would be the most spectrum efficient and would provide communication and surveillance and also navigation services with a single system.
Okay, thanks.
I completely agree with Klaus-Peter has already said.
Okay, thanks, Coretti. I do have another question for you, though. You're not getting away like that. One of the very first questions that came in is that I'm reading out. So it's from Jean-Marc Loskos about what do you consider that LDACS can provide reduction of separation minima, which is usually related to surveillance and not communication. So that makes sense, but I'm wondering if there, maybe from future operational concepts, you see another need for more data exchange from an ATC perspective that will enable the reduction of separation. Any view on that?
Well, it was a suggestion, but you can see that the LDACS have a lot of potentially, because it can be used not only for communications, but only for navigation and surveillance. And thinking about this advantage or this future use for LDACS, we could consider it could be an option. But we will see in the future if it is possible to take advantage of this functionality. But it was the point of the presentation to explain or to express that this is a possible advantage.
And to add to that,
I guess I would also make the link here to the trajectory-based operations, right? So the EPP
right.
downlink, the uplink of complex clearances.
That's what I was going to make. Indeed, the trajectory-based operation is seen as a way forward to increase capacity, and this is a much more data-demanding environment than today's one, because negotiating 4D trajectories between the ground and the air needs quite some capacity and reliable and performant data links, and LDACS can provide that. I personally have my doubt that the legacy VDL Mode 2, which is based back in the 1970s, so it's roughly 50-year-old technologies, can do that. It's simply not suited for such a thing on a long run. It's fine for an initial step, but most likely not if all operations will be trajectory based. We need something much more performant in such an environment, and this will reduce separation and increase capacity at the end.
Okay, thanks. Maybe slightly related to this, there was I remember that there was one question about AP&T for oceanic and polar regions, where that actually may help in enabling a different concept from procedural separation of oceanic. Is that something that we can expect from LDACS? Or is that a complicated question?
It's really complicated because, in principle, LDACS is a terrestrial system. I know there are some thoughts about enhancing that, but I would leave this really to the R&D domain.
Yeah, that's why actually I wanted Okwari to be on stage, but he doesn't show up.
So Ruben, I can comment on it a little bit. So there is some research work going on for LDACS air-to-air development, which is however, on a different technological readiness level by now. So there is work going on for an LDACS air-to-air communication direct between aircraft, and having this established, then you can think about having also these new applications in the navigation domain for this LDACS air-to-air communication link. And I think Quarry already answered the question and gave a reference for the guy who asked.
Well, let's leave it to that. We still have quite a lot of people listening in, so I'll continue a bit. The next one is for Simona. It's since you are the project manager of Project 14, so the ICNSS project within our current SESAR program, I saw a question coming up about someone referring to a TSIRS, which was already delivered in the previous wave, and saying, well, if there is already a TSIRS, why are we not implementing? What still needs to be done? What is the research that is still ongoing? What is the standardization still needed? Can you explain a little?
Yes, in the first wave of SESAR, we achieved TRL4 for LDACS. So it means that we have prototype, not product, in terms of all the equipment that composed the LDACS subnet. In this way, we improved the design, and it's true that we have a previous TSRS, but now this TSRS is reviewed by the solution in this second wave of SESAR. Also taking account all the work that was done in ICAO PTT during this year. So now we are working to reach TRL6. That is the phase that lead to the deployment. So after SESAR Wave 2, we have product with TRL6. We have CBA. So all the work that is around the technical specification is ready to achieve a future deployment. It's step by step. So we finish with SESAR 1, first step, and now we are near to the readiness for the deployment.
I guess there's also a difference between the first TSIRS only covering data link, whereas now actually we're looking at the full scope, which also includes the digital voice and the APNT.
Yes, but also for the data link, the requirements are now reviewed and ready for a final delivery. We review all the aspects related to the security, to the authentication, to the encryption, that in the first phase are, let me say, something like proposal, not finalized as final requirement. So also for data, not only included new feature for the data link, but also for the communication aspect, we improved what is expected for the communication part.
Okay, thank you very much, Simona. I'm looking at the time. We are actually now 25 minutes over time, but there are still quite a lot of people connected. So I'm going for one last question, and then we're going to close. It's a combination of a couple of questions that came in, and I'm not going to appoint anyone to answer it because I'm not really sure who to ask it, but maybe one of you has the answer. So the questions are related to, I think in particular, transitional considerations. So what if we have LDACS, but we also have VDL mode 2? So we're not going to have LDACS stations as a big bang all over Europe, all over the world. We'll probably have a mixture of VDL mode 2 and LDACS. Does that work together? Does a pilot need to switch every time it comes over a different country? Is it seamless? What about the FAN 6? So aircraft coming inbound from the US. can they use LDACS on their fence operations? Another question more on the IP side, I guess, which is probably an easy to answer. Does a pilot now need to switch every time he needs to connect to a different ground station? Couple of questions, all related to transition. So pick the easy or the more difficult ones, as you like.
So let me start maybe with the last one, because that's the easiest one. For sure not. It's similar to any smartphone you have today. You will not select frequencies. You are just getting automated connected to the next available one. And the other ones I really like to answer was more or less the first one, when VDL and LDACS works in parallel in a certain area. If you look from a single aircraft, a single aircraft is either VDL capable or LDACS capable, or both, most likely both. So if it's a VDL aircraft, it will connect to the LDACS system. Sorry, if it's a VDL aircraft, it will connect to the VDL ground infrastructure. If it's an LDACS one, it may start at VDL, it may be nominated, informed. So there's an LDACS system around, and like also again with today's cellular infrastructure, both communication partner will agree on the most capable trunk available in the area. So if an aircraft is LDACS capable and there's an LDACS ground station in this area active, it will fall to the LDACS station to get a better service. But that still means depending on the aircraft and on the pilot. It's all intended to be automated, so no human interaction, because this is really something which should be hidden in the system behind and not be taken care of by the controller or pilot.
So would that require a simultaneous implementation of the multi-link on board,
if it's not,
or can it be done independently?
If it's not a big bang solution, that we have LDACS available all over the globe at the same time, then you can go for an LDACS only aircraft. But let's consider a more realistic approach. There will be line fits coming into the market. So in the beginning, there will only be a limited number of aircrafts being capable to doing LDACS in addition. And also there will be only some hotspots like big airports where you have a high demand, which will be LDACS capable, or states where LDACS is required to provide sufficient performance to deal with TBO coming in the future. It's a trajectory-based operation. These are the areas where aircrafts equipped can use LDACS first, but there will be still most likely a lot of areas around, like far north or remote areas, where LDACS is most likely, from a capacity point of view, not needed for quite a few more decades. It's Central Europe, it's East Coast US, it's high dense airport where we are running out of capacity and where we having performance issues. There is still some area, a lot of areas where this isn't the case. And there, in my opinion, the old infrastructure will serve us already well nowadays and will do so for a while. And this is also protecting our investment.
Okay, thank you very much. Anyone, anything to add on that?
Perhaps 2 sentences regarding the multi-link, since in the working group I in ICAO, they are discussing as one option to use for very safety critical application a kind of simulcast. That means transmitting over all existing links the message. That means duplicating or triplicating the message. The reason for that is to avoid that you have undetected link loss errors, and for that you say, okay, if it's very critical to use all of them, which means that all of these links should have more or less the same capacity, because if there's one of them is a very small band link, like for example VDL Mode 2, it will be I would say the limiting factor, and for that LDACS would be required in a multi-link environment. Regarding the transition concept, I'm saying the VDL Mode 2 or LDACS, using VDL Mode 2 LDACS in an aircraft which is capable of both, it would be similar than in the mobile communication. If you have a mobile phone which is capable of GSM and LTE, it would use LTE in the cities, and it would use perhaps GSM in the mountains where LTE is not available, so we will always choose the better one. And this is similar here. The aircraft, of course, needs to receive scanning both, always both technologies, and if LDACS is available, it would choose LDACS. And if VDL 2 is available, it would choose, only VDL 2 is available, it will choose VDL 2. For all the other equipped aircrafts, if there's only VDL 2, there is anyhow no choice.
Okay, thank you very much, Bernard. And with that, I think we need to conclude. It's now 5 o'clock. We did pass what I mentioned as the threshold, 150 people still listening in. So we need to conclude. I would like to thank the audience for having had the patience to listen in. I hope you enjoyed. I hope you filled out the poll as well. Beware that the recording will be very soon available, I think within a couple of hours, on the SESAR website. With the presentations probably added maybe tomorrow, the Q&A, we're going to take a couple of days to fill them out, to complete them, and that will be uploaded next week on the SESAR website. I would very much like to thank the speakers here, plus those that supported, those who were backing up in answering the questions. Many thanks for your contribution here. I think it was a very valuable, very detailed, very high quality webinar that I saw today, and I really appreciate that. The next webinar is on the 1st of July, so keep an eye on the SESAR website for the announcement, although probably you'll also get an invite anyway. See you there. Thank you very much, and have a good evening.